Okay, so pretty much a private lesson today. No problem with that. So I want to recap a bit what happened on the previous lecture. We defined categories, okay? We changed the definition during the class. We started in a kind of more set-theoretic and dynamic type-theoretic way, and then we made the things make more sense with better types. So we started saying that we have like a collection of objects and a collection of arrows, and two main operations, identity and composition, and we also considered source and target as main operations. And gradually, we ended up saying that a neater way to say this is that I need to specify the objects, and for each pair of objects, I need to specify the collection of arrows from object A to object B, and I have a family of identities. I use A as a parameter here, that the type of them is like an arrow from A to A, so I don't need an extra law to tell me that the source of the ID is the ID of A is A, and similar things for target. And similarly for composition, for each three objects, I have a composition that works like this, takes arrows from B to C and arrows from A to B, and gives you back arrows from A to C. We saw how we can write this as dependent types. We'll skip this now. And there are only two laws essentially for categories. Pretty much they say that identity deserves its name. It behaves as a left identity and as a right identity. But be careful, it's not the same ID here. And the other law is that composition is associative. So the examples we've seen are some very small and basic examples like 1, 2, 3 was a homework and somebody did it. I think Arati did this. And then we also met the category 0, which looks like that, doesn't have anything in it. We talked a bit what it means to be freely generated, but we will redefine this properly within categorical terms in a later lecture. And we've seen also the category of integers with two different relations. So this one would be how, when you consider the relation to be the less than or equal to, and both of these categories are called thin because all CABs here are sub-singletons, which means they have at most one element. So you can think of them like checkpoints that mark that I can compare 7 to 12. You don't get to ask why or in what sense these are comparable. And the other one is like with divides, the same thing, and we deduce that actually there's nothing special about less than or equal to or the divides and nothing special about the integers. We get a construction of a category out of any proset because essentially the only things we needed was reflexivity and transitivity. So this was the first neat construction that takes us from prosets to categories. Give me any proset you like, and I can look at it as if it was a category. So the laws, we get them for free, and what we need to verify is that indeed we have identities and we have the compositions, which means that essentially you need to verify that there is such an arrow to be the identity, and you get that thanks to reflexivity, and you need to verify that if you have these two arrows, this is also guaranteed, and you have that thanks to transitivity. We met a bunch of more categories based on mathematical structures. Here are some algebraic structures that we have talked about a bit in this course, and in all of them, the objects are models of such mathematical structures. So, for example, in monoids, the objects are all the monoids. How you get from one to another is through homomorphism, which the word, we have defined it uniformly for all algebraic structures. It means respect all the operations. And some more structures that are not algebraic we have met, it's like topological spaces with continuous functions, and prosets and posets with order-preserving maps. A similar idea to the preset, give me a preset, I'll see it as a category, was with a monoid, give me any monoid you like, we will see it as a category, and here the story is quite different, because we single out this happy guy or some other object you like as a single object in this category, and all the arrows, which are endo arrows in this case, we take them from the monoid, and again we get for free two of the things we should verify. Sorry, not for free, but we get them from the laws of the monoids. The monoid essentially has the same laws as the category. And the last one that I stated it, but I didn't go through it, and through the details, and I will not go through the details. It's the simple idea of get a category and just flip all the arrows. I'll just mention something about this. Maybe some things will make more sense if instead of, let's say, you have this in category C, in COP, you will want a different arrow. You could flip it and say, okay, if this is the arrow F, then the AOP is the same thing, the BOP is the same thing, and what is the FOP? The FOP is the arrow that corresponds to the F, but it's flipped. Or you could just this is not very standard, but you could look at the same arrow and visualize it as if it's pointing the other way. If it's the pointer, it's this big middle finger here, and it's pointing the other way around. This will make some things a bit easier to draw, but as I said, I don't want to go through the details of this construction. One thing I want to mention is that it's involutive, so this thing ends up being something. I haven't considered equality yet between categories, but if you flip all the arrows twice, you end up in the same, whatever that means, category. So finally, I'm in the position to give some categorical definitions and start appreciating that the setting that we have with categories allows us to define a lot of things. That, yes,
The arrow before shouldn't be the other way, or am I missing something?
You mean this arrow? Yeah, this is what I'm saying. Visualize it. Usually we visualize arrows pointing this way here, right?
Yeah.
Visualize it as if it was like a sword or something. You can visualize it like it's pointing this way. I will not add an arrowhead here, but it's not very common. Once you get used to it.
Instead of thinking that the arrowhead designates the target, it designates the source.
Yes, exactly. But in fact, it's more usual to actually draw it the other way around. You pick your favorite way. You'll see in one of the homeworks, if you attack it, I think this will make the way of thinking about it easier. If you just mentally think that the arrows are pointing the other way. What would be a categorical? I'm trying to meta-define what categorical definition means, and it's something I define inside the mathematical world. Remember, this is another nickname for the word category, that uses only the interface and the things that categories guarantee. So, for example, if I say that a set, let's say, is a singleton, welcome. Usually, the way we would define this would be to say something like, there exists a unique X such that X is inside S. So if you remember, like a couple of lectures ago, we were wondering how we can define some things without points. And maybe you were left with the impression that this is just some kind of exercise in, I don't know, functional programming or something like that. I'm trying to find the thing we had. This was the example. So somebody would define a function like this, which uses points. And when I say points here, I mean these things. So you need to enter the domain of something and mess with these dirty details and say what happens there. And this was pretty much my main argument of why you may not want to do it. While instead of giving this definition for this function, you could say that f is the doubling of the successor of the square, which corresponds exactly to this. And notice that here I don't need points. And I want to do the same thing, like get rid of points when I live in set theory, and I use points in set theory because I have this principal relation. So I want to get rid of these things, because anything that I can express without points might be actually expressible in a more general setting in other categories that lack points. So let's see. We'll see some examples in this lecture. So, okay. Yes, like this, or maybe things like what it means for a function to be injective. Usually, you will define this like this. You have some function from A to B, and you will say that this is injective if for all x and y in A, I'm writing like a set theorist now. You will have fx equals fy implies x equals y. So it's the same thing. I want to give point-free, not just definitions of functions, but actually point-free definitions of ideas. What it means to be injective. I want to be able to say something similar to that, or something better than that, without messing with the data. I don't have access to these little points here. I don't have access to exists. I will start with some. So we'll read these points, but I will start with some definition, quite simple to state, and I will say what it means for an object to be a terminal object. So I'm in a category C, I don't need anything else, and all these definitions will be like that. And I have an object T, and I will say that T is terminal. And what this means is that for any other, or not necessarily other, but for any object, let's say X, there exists a unique, I will draw okay. I don't want to write a formula here. I will place my object here, and I will say that now for any object X, there exists a unique arrow from X to T. This is what it means to be a terminal, and that's it. I just gave a categorical definition, and now it makes sense to see how it incarnates itself in some of the categories we have met. Be careful, the fact that the notion means something in a category doesn't mean that it exists there. So for example, it makes sense to ask in the world of integers with a usual order if there is a list element, because the notion exists there. It happens that there are no list elements of this set. So the good news is that these things make sense, so we can ask them, so we have names for them, and we can use them and visualize them, and have useful notations for them, and look for them in any category. That does not mean that they will be there. Okay, so any question about what it means to be a terminal object so far? Okay, it's just, be careful. I need an arrow, and it needs to be unique. Okay, so let's look at some of the categories we have met to see if they happen to have terminal objects. I'll start with the category 1. Let's remember it's this one, and it just has one arrow. So does it have a terminal object? Somebody help me. Yes? Yeah, the bullet is a terminal object, indeed. Pick any object you like, you only have a choice, it's a bullet. Is there an arrow? Yes. It's the identity. Are there any other arrows? No. So you get it. Similarly for 2, for the correct definition, let's say, of 2, because we had like 3 definitions for a possible 2, which will be this one. Again, it has a terminal object. I hope you see it. It's this thing. And now let's see something different. Let's look at the integers with this relation, with the divides. Yes?
You don't draw the identity, it's always there.
Yeah, the idea is that since they are always there, convention, we will never draw them.
2 has the terminal with itself has the identity, so it's okay.
Yeah, these are implicit. Okay. So about the integers with divides, does it have a terminal object? Ideas. So what are the objects here? It's good to translate the definition like that. It means that, let's say, T is terminal means for any object x, there is a unique we tend to denote unique arrows with this bang on top of the arrow. And another convention that I think I have not mentioned so far, which is very standard when you work with diagrams, it's usually you want to look at diagrams on two stages, because you have something for any diagram that looks like that, certain new things are guaranteed. And since you're not usually recording a video, which I'm doing right now, you need some way for someone to understand what came first and what came after. And the idea is that the dotted arrows or the dashed arrows denote the ones that came after. So when you see a diagram that has dotted arrows, and you don't have a video of it happening, being constructed, the idea is that you consider this like that, and you say for any diagram like this, there exists an arrow like that. So it's these two stages. Okay, so if I take this thing and I translate it into this world of integers with divides, it means that some, like, let's say, the object t is terminal, this was missing here, if blah blah. Okay, what does object mean here? Yes? Integer. So this is like the integer t is terminal if for any integer x, so I should be doing that like that. Okay, there is a unique arrow. What an arrow means in this category? Yes, it divides it. It's a relation of divides. And so this unique doesn't make sense here because it's a thin category. An integer either divides or does not divide. It doesn't make sense to ask in what way it divides it. So this whole thing becomes x divides t. Right? So now maybe I can see it. What is the terminal object in this category? Yes? It's the 0. Okay? And if... very good question. Hold your question for like 1 minute. If we realize what's going on here, we see that the same reasoning would work for any proset or poset, a category that comes out of a proset. So our answer to this question is yes, it has a terminal object and it is 0. Does it have any other ones? If you think about it, it doesn't. Okay. But I'll have more to say about this. So let's get to this question, to this category, the category out of this proset. Can anybody see the answer? What would a terminal object means? Object still means integer, so this part is the same. It's not the bottom. Maybe it's called. Look at how it's denoted. Okay, actually the T is for terminal, but it's a pun. It's simultaneously terminal and top as well. Okay, so here it means for any integer x is less than or equal to t. So essentially we're discovering that if your category comes from a poset, terminal means top, means maximum. Okay, so terminal is a useful concept in posets. And we just realized that we managed to express it in a categorical way, so it may mean something different in some other world. Are we okay so far? Good news, duality, which I have mentioned, is like a 50% discount both on definitions and on theorems and on proofs. So the fact that I discovered the concept called terminal and that I expressed it in categorical terms, it means that I get one for free just by flipping the arrows that I have here and dualizing everything. So, and I also have a free name for that, because as you know, the most difficult part is coming up with good names. So, unfortunately, this is a bad name. But it's good to have a tool, a convention that you get free names, which is just add co in front, to get the dual concept. Let's dualize it. So it means that my initial diagram is like that. Okay, sorry, without this, forget this. So T is terminal, and I will probably want to change the letter there because I don't like T for the coterminal thing. The initial object is like that. It didn't have any arrows, so I don't have any arrows to flip. But the existence once was an arrow, so I need to flip it, and now it looks terrible. But it's still the same thing. And so now you know that dashed arrow or dotted arrow means there exists if all the rest already exists, and that bang means uniqueness. So flipping it, I reach this concept. So in this way, sorry, this would be the coterminal. I don't like the letter T for this. Suggestions for letters. The name we give it actually is initial. So suggestion for letters that for symbols that it's not T. Somebody? Yes. Okay, it's a good thing. Or maybe I could denote it like that. Flip it upside down since it's dual, and since, as you can guess, it will happen to be the bottom in case my category is a poset. So the same question, I don't want to go through all the details here because we are spending a lot of time in the most basic things. But the important thing is, I found out an interesting concept and I got one for free. And I don't even have to think of a name, and in this case I will because nobody calls this coterminal. If I had came up first with the initial idea, I would call the other one co-initial, and someone would say, come on, please, let's find a name for it, let's call it terminal. I hope the words terminal and initial make sense, right? Okay. So, these diagrams are not so interesting because the initial phase of them doesn't even have arrows. So, you cannot really appreciate the amount of things you can say with diagrams so far. So I want to give like a next definition. Actually, before that, I want to examine these two in the category of sets. And maybe in the category of groups. Let's start with sets. So the question is, in this category, do we have a terminal object? I will do the same thing. Since it's like the first time, I should have written it with like better handwriting, if I'm copying it so much. So let's replace what we need to replace.
Is this simple full sets?
No, wait, you are too eager. First of all, let's translate it. What does object mean here? Set, thank you. Come on, let's wake up. The set is terminal if and only for any set. There is a unique, now what does arrow mean here? Okay, that's why, okay. I got what you meant now. This is not the category of set, which is a good reason to appreciate that what really makes the difference in categories, the first protagonists are the arrows and not the objects. So what you're thinking of is like some power set A together with this relation, and you're looking at it as a poset, and all these things that we define, it will be homework to realize what they mean there. What the terminal means there, what the initial means there, and all the other notions that I will define. But I'm not talking about this one. I'm talking about the category called set, which unfortunately is called set instead of functions, because the traditional ones to take the names out of the objects and not out of the arrows. So the objects are sets in the arrows, and the arrows are functions. And we've seen that you could restrict it and like look at the category if you only take injective functions as arrows, but this is not called set. The category called set is sets with functions. So here it means that there's a unique function that goes from X to this mysterious T. Can anybody tell me if in the category of sets there are terminal objects? Manolis, yeah. No. Anybody wants to pick a fight with Manolis? We should. It's a rare occasion. Thank you, Lazaros. Yes?
The empty set.
The empty set is a popular choice, but he will fight back.
It's not because for any non-empty set there is no function.
Yeah. So if you pick... Wait. Yes. Okay. So if you pick the empty set, it's a popular first choice to consider it as a terminal thing. It means that if Manolis picks any set he likes, you should provide one function, and even worse, it should be unique. You cannot find a function from the natural numbers to the empty set. You could, if you change the category and change the arrows to not mean functions, but mean what functions mean in programming, which is partial functions. So if it were partial function, maybe you're more used to the word this is unfortunate. When we say functions here, we mean total functions, okay? So pick any set that has any element. You don't even need an infinity of elements like the natural numbers. Pick this guy, this set, the singleton of the happy guy. You cannot have a function from this set to the empty set, because you need, to be a function, you need to define it for all its members, and where will you map the happy guy? No choice, okay? But one also already observed that actually the empty set serves as an initial object, because in fact, if you give me any set, I can define a function getting out of the empty set to any set you like, because essentially, to define a function from the empty set to any set, I need to specify that many answers to that many questions, as many as it has. So it's the f defined by the following equations. No equations at all. I have already defined a function. Okay. And it's unique, right? Because for a function to not be unique, if you remember what equality between functions means, you should be able to provide a witness in which your function with my function disagree on that. And good luck trying to find a witness inside the empty set. Okay? So we have answered the co-question. My question was, if there are terminals, we have figured out actually there is an initial and it's only one. This we haven't argued well about it, but I'll leave it as a homework. Indeed, there is a unique map out of the empty set to any set X. I could tell you something like, I think you should have proved that in set theory. I mean, the next category will be the groups. I will use this thing. I will say, I consider this known from set theory. I could say I could consider this known from set theory, but it's quite essential. So back to my question, and not the co-question, are there terminal objects? Yes?
Initially, I thought no, but now that I think of it, singletons.
Sorry, initial, did I say initial?
Initially, I thought the answer was no.
Yes, okay, initial, okay, yeah.
Now that I think about it, actually singletons.
Singletons, okay, so we have the happy guy and also the sad guy. They are good candidates to see if they satisfy the definition. Let's say, what is the definition? Any set you like, you must have a way to enter this set, do you? Which function? The constant function that maps everyone to the happy guy, and it must be unique. And of course it's unique because you have no room in your codomain to vary your replies, right? So we do have unique. So this answers not very well, but it is a first answer to Sotiris' question if they are unique. So here the initial one is unique. We didn't prove this, it's an exercise. And we know that there are at least two terminal ones, and actually, how many are there? As many sets as you can have, all the singletons, right? This can put any object of your universe of sets here, and you have a terminal object, okay? So it's not unique, but we could say that it's as unique as we could care about. It's essentially unique for all categorical purposes, in the sense that if you have any, okay, what uniqueness would mean here? I will write it like uniqueness in quotes. And it is a fact that any categorical definition, which is expressed through a universal property, I didn't mention this word, I should have mentioned it here. I'll write it down somewhere. I have defined what it means to be terminal through a universal property, in the sense that I'm saying how it sees the world, how it behaves with respect to all other objects and arrows in the category that it lives in. So if you define something in this way, we'll see a lot of definitions, so you'll get the idea of what a universal property is. So if I define something through a universal property, I'm guaranteed essentially uniqueness for free, and uniqueness is in quotes here, it's the categorical uniqueness. It means that any two objects are isomorphic. So if you have T, so for terminal objects, it would mean that T and T prime are terminal. If you have this, then T is isomorphic to T prime. I haven't defined this notion, which is one of notions I need to define in categorical terms, because I will not be able to use this in any category. And I think you can guess this, so I'll open a parenthesis to define it right here. If I have two objects A and B, I will say that they are isomorphic if there exists an F, I will write it like that. There exists this thing such that F is an iso. I'm just pushing back what the actual meat of the definition, because I haven't said what it means to be an iso, but I will define it right now. Anyone has a good guess of what an iso would mean in a general setting? Yes, Sotiris?
One-to-one.
What's the problem with this? If I say one-to-one, I'm thinking of points. One-to-one is like you mean injective, right? And surjective, so it will not...
If you reverse the image, that you get the same, the initial source.
Should not be enough to be like an isomorphism, but the word reverse is very nice there. Yes?
Behaves well in composition, like it behaves the same way, kinda.
Okay, reverse, let's put the two answers together. It's an iso if, okay, F from A to B is an iso, means that there exists an F, let's call it F prime for the time being, that goes the other way. It means that there exists, but obviously I cannot stop here. There exists an F prime, sorry for the mess, such that, and now the idea is the following. It's a very good.
F of F prime equals A and...
Not A, the identity of A. Okay, they allow. Okay, so F, and I think you flipped yes, you flipped it. So it's F prime of F is equal, because you see this is the F prime. So okay, let me draw this. A, B, I have F here, and I have F prime here. And so this is, F is an isomorphism if this exists in the sense that if you do this, and some other one does just the identity, it's the same thing. And if you do this as well, I need both things, it's also the identity. So this should be the identity. I don't get to write this, okay? Exactly because these are actually two different identities. So I need, oops, sorry for that. So I need to make it. I get to write this, however, which is kind of silly because this is the identity of A and this is the identity of B. Okay? So now I have a way to say that something is isomorphism and also that two objects are isomorphic, and this is in any category. So if I translate this back to the category of sets, I find out that isomorphism means what? Somebody help me. Yes, Manolis?
Sets it will end up being one-to-one and one-to-one.
It will end up being two sets in which there exists injective and surjective function, and bijective function.
Yes.
So the isomorphic objects are what we call in set theory equinumerous, exactly. So if we go back to all the examples that we had here, luckily they happen to be equinumerous, right? And here it happens to be really only one object because there is only one empty set in the world of sets. Okay, questions? Good. So I have enough things. Since we started very late, I think I will either skip the break or make it very, very, very short. But I need to give at least the next definition. And I want to capture this idea. Usually I avoid the category of sets for intuition. But let's see how the set theorist would define this. you would say something like it's the collection of all, and probably you have some ordered pair construction. You pick your favorite one, like Kuratowski or some other one, I don't know. It doesn't really matter. Although, to answer certain questions, you will have to look at what you picked. And you generate like this set, the set of all pairs. And there was a very ancient homework, like from my first class or second class, only for people who have seen set theory. And I asked what are the specifications of these things. And I think nobody answered this. It's common to see something like, okay, I need to have that A, B is equal to A prime, B prime, if and only if A is equal to A prime and B is equal to B prime. We saw actually that from our construction, the type-theoretic construction of pairs, this is a theorem and not a definition. And so let's accept this challenge and try to define this as in a way that doesn't use points. Where are the points here? Here they are. I'm using the membership relation. It means I'm getting my hands dirty. I want to define this idea of the product in a pointless way. Okay, so let's see, and it's quite meaningful to do that. I will give you this definition. So it's called a product indeed, and let's see what the setting is. I'm starting obviously with two objects. And I want to say what it means that a certain object is a product of these objects that I have. So first of all, in order to be a product, let's call my product P for the time being. In order to be a product, a good candidate for a product, you must, first of all, have a way to get out of yourself 2A and 2B. And this happens with the usual Cartesian product, and the product that we have in type-theoretic development we have done so far, it's the out left and the out right, the first projection and the second projection. So in order to deserve the name that you are a product, you have to come equipped with these two arrows. And it's quite easy to forget this and think that this is a candidate for the product. No, this is why I painted everything blue. This is a candidate for the product. And the idea is, like other definitions that we have seen, that you have to be the best candidate of the product. So let me draw another candidate of the product, of being a product. What does that mean? Let's call it C as we're used to. But in order to be a candidate for a product, it means that you come together with two ways of reaching A and reaching B. And the idea is that I want to pick the best of these candidates. So here comes the tricky part, the essential part of this. Any candidate is worse than mine, or mine is better than any candidate of yours, if I can get from the orange thing to the blue thing. So I would like to emphasize this somehow. And how do I get from these orange things to the blue things? I need an arrow that goes from C to P. This so far is quite easy to guess. This is why I haven't asked you about it. And it must be unique. There exists a unique arrow, and I'm not done yet, because it's not just this arrow that gets me from the orange thing to the blue thing. Think of it like elastic thing, I don't know. I need to take in account all this space somehow, and the thing I want to say is that that makes the diagram commutes. I don't want any arrow. I mean, if I had given you a specific set here, you could pick a silly arrow here that maps everyone to some guy here and say, aha, so there exists such an arrow. No, the point is that this arrow must fit in well in the rest of the diagram. And fit in well with the rest of the diagram means that it must make it commute. Think of it as expecting something to go there, flow there in a certain way, and you will consider these to be valid if this is equal to that, and if this is equal to that. And if such a thing exists, we tend to call it, to denote it like that. And we tend to give some indicative names for that, like, I don't know, out left and out right. Or P1 and P2, or dot 1, dot 2, or P0 and P1, what have you. Okay, first, second, whatever. So question to have a very tiny 5-minute break. Let's investigate this concept in one of our categories. Let's see the integers with division.
Can I say something?
Yeah, sure.
about this?
Uh-huh.
Is it okay to say that, in effect, the fact that P exists is that if any object C has maps to both A and B, it doesn't really do this in its own way, but it always goes through P.
Yeah, and that's a very nice phrase. Essentially, every candidate goes through, factors through P. So if you have some other candidate here and you think you evaded P, okay, maybe you have your path here, but essentially this path is this path, and this path is this path. Thanks for the comment. So let's see it in two categories. First, this one. The rest will be homework, of course. So let's translate it. I'll try to do this quickly. And now I will not say the object P is, because the whole blue thing is, if it's a product, it's the whole blue thing. It's P with these things. So maybe I should say, like, the diagram, this whole thing is a product, and here I have implicit A and B, is a product of A and B, means for any this thing there exists a unique map. There exists a unique, I didn't give it a name. I will write like that. Okay. I will not rewrite it. I will just. I just want to translate it in the integers. So let's translate it. What do I get as a candidate of being? I almost said the wrong word here. A product of two integers in A and B. First of all, it needs P, which is an integer, must have arrows going to A and to B. I'm in this category. So what does that mean? Let's translate this information. Yes? P divides A and B. So first of all, I have P divides A and P divides B. I have a name for that. It's a common divisor. So this is the form that I have guarantees that it's a common divisor. But now I need to say that it's the best of all those things. And what does that mean? For any C, which is also a common divisor of A and B, mine is better. And what does that mean? I have an arrow from C to P, so C divides P. And I have just found out that this concept I already knew since high school, probably, which is what? Okay. So the concept of a product exists in this world, and it incarnates itself as what we call greatest common divisor. If for some reason we hadn't discovered greatest common divisor before discovering categories, we would say, aha, that's an interesting concept here, let's give it a name. And maybe it would be a normal name to give. Questions? Okay, so what about the category? No, actually, it's a good time for a break. We'll only have a 5-minute break because we were too late to start.
Sorry,
Yes, sir.
is it guaranteed that the product will always exist?
In any category?
Yeah.
No, it's the same thing. Any definition that we'll give, unless it's a very silly one, actually I cannot think of anyone that would be, because you even have the empty category, right? It has no objects and no arrows. So all these definitions, categorical definitions through universal properties, the only thing I can say about them is that if they exist, they are unique, in quotes. So the uniqueness of the greatest common divisor here means what? If you have two greatest common divisors, and you can have, because forget the idea that greatest means something compared with this order, it's something compared with this order. This is the only order that matters when you do this number theory stuff. So, like, you can have -2 and 2 both deserving the name and being greatest common divisor. You don't have uniqueness, but you have uniqueness because they are isomorphic. Because here it means divisibility cannot distinguish between them because it sees both these arrows. Okay, one is less than equal to the other. Okay, so let's take a 5-minute break.
Στο μάθημα σου λέω ότι είσαι ένα σύνολο και έχεις συνεισέψει και ωραίους και λες, εσύ κάτσε όλα όσα κάνω, κατά κύριο λόγο απλά χρησιμοποιήσω ότι έχω μια πράξη και 2-3 ακόμα ιδιότητες. Και πας ένα βήμα πίσω και λες, σταματήσω να μιλάω για ωραίους, κρατάω μόνο αυτά, παίρνω ένα σύνολο με στοιχεία και αρχίζω και παίζω και λέω τι μπορώ να βγάλω. Και καταλήξει με την ομάδα. Κάπως έτσι και εδώ, πάμε ένα βήμα πίσω και προσπαθούμε να πετάξουμε οτιδήποτε δεν χρειάζεται. Στην περίπτωση καταλήξαμε με αυτό. Η γενικεύεις λίγο την έννοια. Και λέω ότι και το καρτσένο γινόμενο και η τομή και ο μέσος κοινός διαιρέτης όλοι εξηγούνται αυτό το πραγματάκι. Και πώς άλλα ακόμα.
So it's quite unfortunate that indeed the names and maybe the notation usually come from the specific category, the category of sets, because there is some kind of objection or questions during the break. So let's see if this thing, if the Cartesian product of A and B in the category of sets deserves its name. So now we have various times during the lecture so far, we have used the word product and sum and stuff like that, and I tell you we don't have yet the means to see if they deserve their names that we're giving them. So in order for this to be a product, it means that first of all it's not by itself. We need to pick two arrows, and here we will pick the two projections, call them how you like. So they go into A and B, and this should be blue maybe, yes, this is what I usually draw blue. And then, in order for this to happen, I need to have, for any other candidate C, that also comes equipped with two arrows. Let's call them F and G, to be generic enough. My product needs to guarantee that any orange thing goes through here in a unique way, and this commute. So far, all the examples I mentioned were in thin categories, so commutativity didn't really make sense. Because what does this mean? What does it mean that this commutes? It means that this and then that is the same value as this. But I was in thin categories, so I didn't have any way to be non-commutative. Because from any two objects, there was at most one arrow. So how could you break commutativity? You would break it if like this arrow was different than that arrow. But in the integers, this cannot happen. It's a thin category, right? From C to A, there is only one arrow, so you get commutativity for free there. It's automatic. Here, no, because it's not a thin category. So let's see what this function would be. Let's say you want to defend the idea that this whole thing is a product. You should define this function and you should prove that it's unique. So first of all, let's call it, I don't know, for the time being, let's call it H. What would the definition of H be? You are doing set theory now. You are a set theorist inside the world of sets, so you will mess with points and you can say, okay, H of C, I will map it to a pair. In which pair will I map it? Okay, you need, and the same thing actually would work even in the category of types with the products we have seen. It's essentially the same thing, the same idea. Where should I map it? I need something of type A and something of type B, or set A, sorry. Where do I get it? I have a C, and I have a way that maps little c's into A. So let's use this. Yes, it's F of C. And here is G of C. Okay, so I'm done with the existence part. I guaranteed a set, an arrow here. And now what about uniqueness? It has to be, what about commutativity? So what does commutativity mean here? It means that if you do the projection of the H, so it's like P1 of H should be the same as F. And what does equality of function means? Well, you give them a point and they agree on this point. So C is equal to F of C. Check this for every C. Let's see what this will be. You start from a little c here. It gets mapped through H to this pair, P1C, P2C. Oh, thank you. F. Now project out of it the left part, so you get F of C. Project the right part of it to get G of C. And now see the alternative. This one goes to F of C. It's equal, right? And this one goes to G of C. So it commutes, and you have to check the uniqueness, which comes from function extensionality here. So you do have, so indeed, the Cartesian product in set theory deserves its name. It is a product of A and B. Are we okay so far? Good. So let's practice our dualization skills. Let's see, because I said for any concept, interesting concept we find, if I flip all the arrows, I get the dual concept. So this would be called the coproduct, which is the name I get for free. Let's do this together. So what's my initial state? The initial state was just two objects A and B, and this is enough for me to say what it means to be a product of A and B. So this will be enough for me to say what it means to be a coproduct of A and B. Also, a different name for coproduct is sum, which is a much better name. So what was the candidates I was looking at were P's. Now instead of P, I will use S for mysterious reasons. And I had ways of getting out of S and into A and B. So now we'll have the dual thing. All candidates are things from which I can get into from A and B. In a specific way to get into from A and a specific way to get into from B. So these are the candidates for coproducts or for sums look like that. So what does it mean to be the best one? I'm not thinking right now, okay? I'm just flipping the arrows. I was thinking when I was doing products. This I get for free. Again, this will come together with two ways to get inside it from A and from B. And what was the last step? I have to say that mine is the best. All the universal properties are like that. It's things, and they are the best among their peers. So it was an existence of an arrow like this, but now it will be an existence like a uniqueness and existence of an arrow like that. Such that commute means commute always, okay? So let's say how this incarnates itself. I mean, let's do this quite quickly and orally. In the integers, what will this mean? First of all, for someone to be considered a sum in this sense, not addition, right, of A and B, it means that A divides it and B divides it. Okay, so how do we call them? You went to the final answer immediately, yes. So this guy will be the least common multiplier. So the candidates here are the common multipliers, and the idea is for any multiplier, my multiplier is better. In this sense, it means that it divides yours. It's the least common multiplier. Let's continue the oral fast-paced thing. What would be the sum of A and B in in our types? It's better in our types. If you prefer set theory, go to the set world. Maybe we can go to the set world, I don't know. So, any ideas?
For sets, it would be disjoint union.
It will be the disjoint union, and for our types, it will be the sum of the types. So it deserves its name. Okay, we do have these things. They are called in left and in right. or the lefting, or the rightment, or I don't know how you want to call them, in right. So you have ways to go there. So remember this whole business of getting functions for free or ways to produce arrows without messing with dirty details. This H name here is completely non-informative, and it doesn't take into account that it only depends on the orange thing. On the other hand, I gave a nice name here, which shows that clearly this whole business depends on A and B, and I call it the product. I need a name for this function, because I want to be saying, consider the function, the obvious function, the unique function that goes from here to there, thanks to the fact that it's a product. So I need a notation here. And the notation came up in Zulip a few days ago, like 2 days ago or something like that, mysteriously. And I will use this notation, FG. There is a class, I could call it like, this is called the pairing of F and G. Why do I have the right to give it a name and to give it a notation and to give it all those things? Because it's essentially unique. It's actually unique, and it depends only on the arguments that I have here. So if you have any configuration like that, the diagram guarantees that there is a unique thing like that, so I get to give it a name. And I will call it angle brackets FG angle brackets. The clash is that we also use the same brackets for a different thing, which is just a pair of things. So maybe I should avoid it, I don't know. Maybe I should use it like, maybe I should use parentheses here. The context is always makes it clear which thing you mean, okay? But if you have, just a second, if you have like two functions like that, you have an F and you have a G. Now, sorry, and if you have an, okay, if you're like that, actually, and if I tell you, what about this, it's not clear technically what you mean. You could either mean the unique thing guaranteed to go to B cross D and make this thing commute and blah, 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 which is what I just defined. You could mean the pairing of F and G, or maybe you want to consider them as pairs of two functions. So one possible thing is that this goes from A to B, D, so it's a function from A to B cross D, and the other interpretation of this thing would lead you to a different type. It would mean that this is just a pair of functions, one from A to B, and another one from A to D. But thanks to the context you have, you always know what type you're expecting to see, so you will never have a conflict there. It's like a polymorphic notation. If it shows up where you're expecting to see two functions, one from A to B and one from a pair of functions, then it's this one. And if you expect to see one function from A to the product BD, then it's this one. So I don't really need a different notation. Similarly, I should give a name to this one. And there are like two names that I will be using in this, the whole of this course. It will be either this, F or G, or this. This is supposed to be a curly, just two different notations for the same thing. The idea is that essentially you will pick which of the two functions you will call depending on if the thing you have here is a lefty or if it's a righty. Okay, if it's a lefty, you call this one. If it's a righty, you call this one. We've seen this function before when we're talking about the sum type, and now just universalizing, abstracting this notation so that it's applicable in any category that I have. So, certain universal properties are characterized by the fact that they tell you how you get out of things, out of objects, and others how you get into objects. The dual one will flip the situation. So let's do some kind of maybe simple exercise. Let's say I have some types. Let's say I have this. I want to go from this to that. And the idea is that I have maybe some functions lying around, and I don't want to get my hands dirty and start messing with points and say, it's the function that takes the little a and little b to that and all this. I want to define it using archery, which means I don't want to get inside the forest of things from the outside, external diagrams only. And let's say I want to define a function like that. The fact that I'm leaving a product is completely useless. I'm getting out of a product, but products don't help me get out of them. If you see the definition of what a product is, it guarantees ways to get inside it. So the fact that this is a product is not going to help me at all. The fact that this is a product helps me. Okay. Similarly, if this was a plus, now the fact that I'm entering a plus type, this kind of object, I don't get any help from the fact that it's a sum. I get a help from the fact that I'm leaving a sum. Okay, so let's put them together and let's try to work like to build an exercise together. Let's say you want to go from here to here, and let's start breaking it down to all the help you can get. So the object is to go from A plus beta to gamma cross delta, okay? So the desired final arrow will be some H arrow here, which I'm hoping to define in a way without getting my hands dirty, okay? So you have a choice here. Do you want to ask for help from the product or from the product or from the plus, from the sum? Pick one at random. Somebody help me. Make a random choice, it doesn't matter. Product, thank you. Okay. So how does the product help you? First of all, you have to remember that the product comes together, whether you want it or not, with two projections, which is the out left and the out right, which gets you to gamma and delta. And you say, okay, and now you can remember what kind of extra tool you have if you want to find a way to get inside the product. It says this will end up being the dotted arrow, so it's sufficient to find a way to get into gamma and into delta. And this may seem like not a big step, but it's a huge step because you have the problem. Let's say you want to solve this problem to go from here to there, and maybe this is kind of complicated, so I have simplified it. I just want to find a way to get from here to here and from here to here. Okay, so it's kind of, let's say, good news. So it's enough, it's sufficient to go to here and here. And now I can get extra help. What can I do now? Because I have reduced my yellow problem, which is a big problem, let's say, complicated problem, to two simpler ones, the blue problems. Now let's look at the first blue problem. Where do I ask for help?
Split the sum.
Split the sum. Okay, I like the phrase. The fact that I'm getting out of a product means that, let's remember, out of a, I said product, it's out of a sum. Let's remember this is not by itself, right? So I have an alpha here, an alpha here, and a beta here. I hope this makes sense. And these are the left man and the right man, the in left and the in right, okay? So in order to define something that goes from the sum, from the sum to delta, it's sufficient to provide two functions. What are they? Anybody?
A to gamma and beta to delta.
A to y to gamma to delta. We are trying to solve this problem now. I want to go from here to here. So the sum tells me if you find a way, I know a way that I go to alpha and to beta. Okay, so if I have a way to, have I drawn anything wrong here? I think not, right? Okay, so if I have a way to go from alpha and like that, I can put this together, and because now gamma looks like a candidate for a sum, and the sum is the best one, so it will give me for free this one. So let's say that I need a function. I should give it a different color, maybe, like, okay, solve the orange problems now. And the idea is that the orange problems, I'm kind of happy, right? No, sorry.
No, you need from beta to gamma.
Yeah, I'm mixing something here.
Just solve the upper blue one.
Yeah, thank you, okay. So let's call them, I want to mess with my notation. I will call this U and I for some reason that will be apparent later. Okay, so I have reduced, and I'm not done yet, right? Because this will give me this blue thing. I need the other blue thing as well. I will take advantage of the same thing. I'm getting out of a sum, so how can I do it?
Same thing, beta to delta out of blue.
Okay, so I need, let me not be confused here. Okay, so I will make it purple. So if I give a way to enter the delta from alpha and from beta, I can put these things together. Okay? So what are the names I want to give to these things? Will be V and J. And let's see now, what is the blue arrow? Now I know the name of the blue arrow. I could call it something like initially F and G.
It's like sum of
Yeah, so
I and
exactly. So this one, the top one should be it's U or I, and the other one it's what? It's help me here. VJ or JV? VJ, okay. Okay, and now what is H? It is the pairing of the two blue ones. It's called the pairing. Oh, yeah, okay. So yes, what is this one? So it will be like U, I, VJ. But all this construction here happened thanks to the random answer of Sotiris, who said, I want to ask first for help from the product. Okay, what would happen? What?
50%.
Yes. So you could say maybe you started the other way around. So what would happen in this case?
What's the first thing? What are I and V? How do we know we have those?
No, for V and I, like the ones that still have a single letter, it's U, V, I, and J. It's not like that you have them, but you have reduced the complicated problem of going from this complicated type to this complicated type into 4 simpler problems. You still have to solve them. I'm not saying that they are guaranteed, but it's much easier to define these little simple functions. Like if you can define functions from alpha to gamma and alpha to delta, beta to gamma and beta to delta, you get to get this thing for free from this construction. But what would happen if you do like the same thing but in a different order? I don't want to do it. I want to leave some things like for you to figure out, but let's just start it. So I don't want to, there's a danger that I will do the same thing. So now I will ask for help first from the sum. So it means that the fact that I want to go from here to here, which is a new h, let's call it h prime, that I want to define finally. First I will want to say, okay, I'm leaving a sum. So forget about the fact that it's a product. What can I take into account now?
you need to take A and put it into gamma left.
Exactly. Okay. So if you find a way to get inside here, this starts looking like a candidate for a sum. So it means that the fact that this is a sum will give you a function for free here. Okay. And now we'll do the same thing. In order to solve this blue problem, I will take advantage of the fact that I'm entering a product. Okay. So moral of the story is, if you are entering a product, that's good news. And if you are getting out of a sum, that's good news. The other way around, it doesn't help you at all. Okay. Good. Any questions? So essentially, so this is the main exercise here. So I was saying that we're constructing together exercise. What will the final thing be here, and what is the obvious exercise? So the final thing here will be like the co-pairing, okay, of two things, which in this case will be it will be U. What is the I here? I don't want to mix the letter. I think it's like I J. Choose here U V. I might be wrong. U V I J. Okay, I will.
First from A and then from alpha and then from beta.
U V I J. Okay, yeah. Okay, so these are not two different ways that make sense. Only one of them makes sense. It's the one that Panos said. So it's like UV and then IJ. And now the obvious question, and this is homework, is to check if they are equal. Sometimes you see algebraic equations, even in functional programming, that say prove that this is always equal to that, and you ask yourself, like, how would one come up with these weird equations? Essentially, I'm saying that this thing is equal to that thing, and compositions show up as well. And the idea is, if you draw diagrams, you will discover these equations. But we didn't do much thought here, and we come up with two different ways of going from here to here. And the obvious question is to check if they are equal. Any questions? No. Okay. So now I want to go back to the idea of injectivity, and I want to see how we can make this pointless, point-free. So remember, F, we say that F is injective. It means that essentially it means this. What is my problem with this definition? It uses points. I want to get rid of it, because if I get rid of it, I will discover what is behind it, let's say. And there should be like another, if you have any kind of mathematical OCD, which you should have, you should be a bit irritated, because you have like always treated injectivity and surjectivity as if like dual in a sense. But if you see the definition of surjective, it's not at all like that. It's like for any, here let's say it's A and A prime. You go from A to B. And surjectivity would be what? It's like for all B. Somebody help me? Yeah, and I'm already getting creeped by that, right? There exists an A such that what? A gets mapped by F to B. Okay. They don't. You may think that I'm trying to emphasize my point, but even if you like that, they don't look anything like symmetric or dual or what have you. There is a good reason for that. I want to pretend I don't see it for the moment. And I want to say that, okay, this is not so pretty. So let's try to make it prettier. And already we have a difficulty because we have something like, for each A in A, something happens. How do I say that in a category? How do I say that without mentioning points? And another way of attacking this idea, this problem, is to say this looks an awful lot like cancellation. This is, you have, consider that you are in a high school and F and A are like real numbers. You have a cancellation problem, and so this is multiplication now. And it's like, forget that F looks like a function. And this looks like this law that you learned in high school or I don't know where, that you can cancel out the f's. And there is a caveat there that like you don't get it always. You need to be careful. Why? In the real numbers? Yes? Yeah, so essentially, maybe what we're after is like what the cool numbers, the non-zero ones, have this property. So what are the cool functions that have this property? So these cool functions will end up being like the injective ones, but I want to take a point of view of like seeing it as a cancellation property. The problem is that I don't have an operation, because when I write f of a, you may remember that there is an invisible thing here which stands for function application, and you can say, aha, I do have an operation, it's function application. And actually, for this conversation, to facilitate my exposition here, I want to introduce a symbol for that, a specific symbol for that. I will use the at symbol. So this thing that I'm writing is nothing more than what you would normally write like that, f of x. Why do I do that? Because we can write stuff like fog. Sometimes we write this as juxtaposition as well, f of g. And now there are too many invisible things, and I want to make sure that I understand what's going on. Even worse, we pronounce this many times as off, and we pronounce this as many times as off. Although they seem completely different things, right? One composes two functions, the other applies a function to an argument. Still, we pronounce them as off. Okay, so why do I say that I don't have an operation? Because operation in algebra means give me two things of the same type and I will give you another thing of the same type. Here the left thing is a function, the right thing may not be a function, it's an argument for the function. So it's not really an operation just like multiplication was. And now I start saying, okay, let's make it into a function. Let's make it into an arrow. And the great idea here is that anytime you think of a point in a set A, there is a correspondence with a friend of yours who, instead of thinking of this point, which let's make it blue, instead of thinking of that, your friend thinks of a different blue thing, which is a certain function from his favorite singleton. Sorry for that. So pick your favorite singleton, let's call it 1, and it has a single point in it. And now the blue thing is just the function that sends this thing to your blue thing. Let's digest this a bit. So your A has a bunch of things, and you say, aha, I picked an element of A. And in a different world, the world of sets, still it's a world of sets, someone said, aha, I picked, and I called it little a. Okay? So this is little a. Little a should be blue. And your friend on the other side says, aha, I picked an arrow, a function, from 1 to A, and I called it A. And what does it do? It maps the only point on the singleton to the same thing that you called A there. And I'm claiming that the two things are in a correspondence. Is this something that you want to attack, or is it completely acceptable? Pick your favorite natural number, which is 42, and then I will pick the function that maps the only bullet of the singleton point to 42. You don't have any extra information. I do have some maybe only bureaucratic stuff to do in order to get to the actual point. I will need to call my A with an empty tuple, or with a star, or with this bullet, or what has it, in order to get your A, but this is trivial. It can even be mechanized. There is no information. I don't need to think about this in order for it to happen. So for any blue A, your blue A, which is a point in A, I have a different blue A, which is a function from 1 to the big A. So which means that anytime you write something like for any A in A, I can translate this in a narrow only way and say for any Have you lost me, or are you still with me? Yes? Are you, it's okay. So, in order for this to make sense in any category, there is one more thing that I need to have an access to. It is this one. Okay, so this one here is actually, I need a terminal object. We'll discuss more about this later, because now I do need to get to the definition of what the injectivity means. With this mindset, let's remember, and this is one of my favorite things always, let's remember the definition of composition. And I will write it like that. What was the definition of composition in the world of sets? Don't be scared about the at symbol, okay? It's just a function composition. I just want to make it really visible that's there.
F at G at X.
F, yes, at, very nice, G at X. Now, this is the definition of the composition symbol here, right? The composition. And this is very nice because the definition will get promoted to a theorem. All demoted, what's your point of view, but it's actually, how can this be a theorem? Consider what is the shift. Okay, essentially, I should have this thing, right? I know this is equal to that because this is just associativity of what? Of the composition. So if you want your composition to be associative, this holds, and I'm claiming if this holds, you don't have an option for this. This is essentially associativity of what? Of. It doesn't make a difference if you say f of g of x or if you say f of g of x. And I'm taking advantage of the fact that I pronounce them as of, as to indicate that this thing is not as far as we may think. If you start, when you just learn about composition, if you see something like that this is the same thing essentially as this, and maybe Manolis already says this has nothing to do with that, because this is a composition composed with something, it's a composition applied to something, but what is the trick here? Consider that this x is actually a function. Which function? The function from 1 to your thing. Okay, so when you want to abstract this thing and reach finally the idea of this injectivity that I'm trying to, is injective function where the left cancelable, what is the operation? It's the only operation I have lying around in any category, it's the composition. So I will call f, and now I need a name for it. It will not be injective. Finally, it's one time that we have a proper name for that doesn't consult the sets, it's called a mono. So we have finally reached a monomorphism or a mono. F mono means that f is left cancelable. Sorry, not f. Yes, f is left cancelable to this with this operation. What is the corresponding diagram? Okay, so I have f here from A to B. And the idea is that you pick two elements in A, but what does element mean here? Pretty much mean any set you like. And I want to generalize it even further. So this is an important generalization. I don't want to make it so that you need a specific point inside that. Generalize it further from any set or other object that you have there, from any domain D that you pick there. So if you have like I and J, if you have this diagram, and if this commutes, what does the commute mean? This is equal to this. So f of I is equal to f of J implies that A and J were already equal to begin with. So any f that satisfies this, it's cancelable by that, on the left by this. I will call it mono, and that's what mono means, what monomorphism means. Good news, I gain a corresponding concept for free just by dualizing everything. So if I dualize everything, it means that the diagram will look like that. Now my f is like this, And now I have two ways to continue after f. Let's call them, I don't know, u and v. And this will be some other codomain now called C. And now the law will be like, if you have, help me here, u of f is equal to v of f. This implies that u is equal to v. And I'm doing this like in a blind, completely blind way. An alternative would be to get the concept of surjectivity and try to figure out how to express that. But I don't want to do 2 times the effort. I figured one concept, I get the other for free. This is called f is epi. Monic is an adjective, epic is an adjective, mono and epi are nouns, okay? So essentially this means that it's cancelable on the right. And if I remember how I proved in high school, hopefully, maybe in high school, maybe in the first years or something, that something is cancelable, a lot of times an easy way to get the cancelability on the left of something if it's invertible on this side. Right? So like in group theory, you prove the cancellation law. How do you prove that? You say, aha, I have inverses. I don't even need bilateral inverses. I could only need a left inverse. So if I have like a left inverse of f, I can apply it on f when it's composed with some I. And then, okay, let's do this little thing rapidly. If I have this, I can get this. I will stop writing compositions, okay? Everything here will be compositions. The left inverse of f, fi. I have the left inverse of f, fj. And there, from associativity, I get this. And now from the fact that FL is a left inverse of F, I get that this is the identity. And from this I get that I is equal to J. So essentially, it's a stronger property to say that F is cancelable on the left, invertible from the left, because from this you can get that it's cancelable, but maybe not the other way around. So I will give the next 2 definition and stop the lecture here. These are called, there's better monos and better epics, which we'll call split mono and split epic. I know that the name can be a bit scary, but this just means that F is invertible on the left, and invertible on the right. And the obvious homework now is, now that I have given like 4 new concepts, thank you, in categorical terms, let's try to figure out what this means in all the categories we know, and if certain arrows deserve this name and not. So we'll find out that, like in group theory, monomorphism is equivalent to injective homomorphism, as you have guessed and we have discussed a bit. And in other categories, it's not the same thing. Already in the monoids, I will not tell you exactly what it is, but it's a hint to look in monoids. One of the 2 things at least will break. So it will be a different thing to say, for example, that it's an epic epimorphism than saying that it's an surjective homomorphism or something within injectivity. Any questions before we sum things up before the Easter? Yes?
I would rather strongly suspect that mono and split mono should be the same, as well as split.
So it's also a homework to figure out a category where these things are differentiated. So the one direction is obvious, so this you always have. I mean, if it's invertible, you can cancel it. And a good intuition where you cannot, you don't have inverse, but you can cancel, although it's just a small hint and not big hint, is thinking the monoid of natural numbers. The cancellation law holds. If you have n plus u is equal to m plus u in the natural numbers, so you don't have inverses, it is the case that n is equal to m. You have the cancellation law, you don't have inverses. right? So if you can prove cancellation law without inverses, you are better off. If you need inverses, you will. If your proof on cancellation law relies on inverses, which is usually the case for groups, you don't get it for free for monoids. So this is not valid in all monoids, but in this monoid it's valid, and even though there is absence of inverses, right? It's not the same thing. It's a very small hint where to look maybe to find the distinction between that. But none of these things end up being the same. First of all, injective homomorphism maybe doesn't even make sense in some category because injective necessitates that things are functions. But even when these things make sense, split mono and mono, split epi and epi, there is a clear stronger and stuff like that. And also, it's not always the case that mono and epi means iso. So this is another thing to find out. Okay.
That is also
Yeah. So like categories there are categories that this happens. Like in the world of sets, mono and epi means iso, not means. Sorry, forget this word. End up being equivalent in this thing, but the meanings are always the meanings we have defined here. So if there are no further questions, we can stop here. Continue on Zulip. I will put a bunch of homework to have something so that you don't get bored in the holidays. Does that make sense? Okay, so see you on Zulip and see you in like 2 weeks.